Okay, welcome back. Um, now, we're going to be looking at the representation of the organic molecules. The organic molecules, just as other molecules, they exist in three dimensions. And what it is that there are equipment that are available with which you can be able to see the structure of these molecules. Yeah. So it may surprise you, for example, if you're going to Google something like the image of atoms. Yeah. It may surprise you that with the current technology you can be able to see the something to call electron ion image of individual atoms. So it's possible to be able to zoom in on the structure of of the molecules. So they exist in three dimensions. Um, there are various structures. What I've done is to make a general view about certain structures which I think you may have encountered, or maybe I think you may have learned through the uh, okay, the bonding of structures. For example, in this case, there is this structure which you're going to call linear. Can you see one? Uh, I'm holding the central atom, and you can see there is a, what color is this? Can you call it what do you call it? Gray or lightish? Okay, you can call it gray. Yeah. So it's attached to the other elements through a linear bond in which the bond angle is 180 degrees. So this structure is going to be said to be a linear structure. For example, a molecule like carbon dioxide is going to be said to be a linear molecule. So this is one of the structures of compounds that you're going to be dealing with, or maybe you may have dealt with in the past. There's another structure which I'm going to show you here. Perhaps, if I may put it like this, you're going to see that the four atoms, they lie on a plane. By a plane, I'm talking about if I've got something like a piece of paper, these atoms can lie flat. So that's what you're going to call something like a plane. So this one is going to be called trigonal planar. What can you say about the bond angles? Yes, you guessed it. They are 120 degrees. So 120 degrees, 120 degrees, 120 degrees, they make up 360 degrees. So this one is going to be said to be trigonal planar. So molecules such as boron fluoride, it's also said to be trigonal planar. Now, there's another molecule I want to show you here. What can you see? If I may have something like this one, and I say it's a plane, you can say it's not entirely flat. So there's a central atom. In this case, let's say this blue one is called nitrogen. Yeah. Can you see it's got three atoms around it, and you can say it's something like ammonia. So it's got maybe a hydrogen, and a hydrogen, and then there is something protruding which are going to call something like a lone pair. So this one is going to be said to be pyramidal, in which you can say this lone pair is taking up a position on its own and is causing these other atoms to be bent down. So this one is going to be said to be tetrahedral, even though it's got three atoms, but the lone pair, it occupies a position on its own. Now, similar to that one, there is another structure which I'm going to show you here. Now, assuming you can say the red one is oxygen, so this is something like a structure of water, and showing two two lone pairs. You can say this lone pair is at this position, this is at this position. So in other words, if you're going to say this lone pair and this other lone pair are on an axis on their own, this one is also going to be said to be tetrahedral in nature. But this one but got two atoms, the rest are occupied by lone pairs. Can you see? So in other words, you can say one lone pair is occupying a position here, and then the other lone pair is here. So this is also tetrahedral in nature. Yeah. So a molecule like water is going to exist like this one, in which there's the central oxygen, and then there are two hydrogens. Yeah. And then the last, and I think before I come to that one, there's another one I need to mention. So this one may not be there in organic chemistry, but I think it's quite important for me to mention here. There is more or less like a planar here, and contains three atoms, and then there is the atoms on the top and the bottom. So this one will be said like trigonal by pyramidal. Yeah, I think you might have seen a structure like that one. But the one which I want to really focus on is this structure which I'm going to call tetrahedral. Water and ammonia, they belong to this group, but this one which I want to illustrate here is this one which we're going to call a hydrocarbon called methane. You're going to look at that chemistry later. Take the black ball as carbon. Yeah, take the black ball as carbon, and then you're going to see the white ones as hydrogen. So you're going to see that the bond angles, it may not be easy to estimate, but in this case the bond angles have been known to be 109.5. Yeah, 109.5 degrees. So this is a structure of an organic molecule. In fact, all the hydrocarbons, yeah, which you're going to call alkanes, but you're going to see it a short while as I'm going to be describing what you're calling functional groups. And you're going to see this molecule which you're going to call methane belongs to something which you're going to call what? Hydrocarbons. Yeah, I mean hydrocarbons are alkanes. You're going to see the chemistry of these compounds shortly. Yeah. So remember, this structure which you're going to be encountering is called an alkane. It's a tetrahedral structure. And in a short while, I'm going to show you what happens if I'm going to add, for example, one hydrocarbon to another. You're going to see what is going to be happening to the structure later. Yeah. Okay. So let me mention something about the functional groups which are going to be dealing with. What is this thing which you're going to call a functional group? Yeah? As the name implies, it is something which is going to give the molecule its functionality. By functionality, it means that it's something which is going to probably either increase the electron density around a certain region of a molecule, or probably decrease. And by increasing electron density, it will mean that if you're going to have an electron deficient species such as a proton H+, for example, like in acidic medium, it's going to be attracted to an area of electron density. You understand? So in this case, something which has got electron density is going to cause species which are positively charged to be attracted to that. And then you're going to see some species which are positively charged are going to cause species which are negatively charged, like hydroxide ions, to be attracted to it. All right. So I'm going to show you something about some of these structures which which I've mentioned here just a short while ago. Okay. Now in this case, I've said what you're going to be studying first in a course, it's going to be called alkanes. What I've done is to send you an email of, or I've sent you a link to the documents related to this course. So you're not going to be expected to look for other reference materials. I've been able to gather all the reference materials plus the lecture notes that you're going to require for this course. Yeah, and get it from me that the examination is going to be based on what you've actually learned, or if there will be probably some modifications, but the concept will be the same, but nothing of a surprise. Yeah, please get it from me. I've taught this course for at least 12 years. Yeah, I'm talking about from is it 12 years from 2008? Yeah, yes, about 12. This is going to be the 13th year. So and many engineering students have passed through me, and they're really proud of where we are. If you can get to your colleagues who are either in 4th year or 5th year, or maybe in the industry, just tell them the experience with organic chemists. They'll tell you they've dealt with Dr. Maniki, and it's been fun. Yeah, so you're really going to enjoy this course. Yeah, all right. So so what can you see here? There is there's something which I'm going to call something like a bend. In this case, it's just an illustration of what I'm calling a double bond. Can you see here? There's a bit bent, but you're going to see more about this when you'll be looking at the chemistry of alkenes. Take this one as what you call something like a double bond, and if I've got something like a plane, you're going to see that this structure is going to lie flat on a plane. If I may raise it up, what can you see? The bond angles here are 120 degrees. So there is 120 degrees, 120 degrees, 120 degrees, 120 degrees, 120 degrees. Yeah. So this structure is going to be flat on a plane. That's what's going to be said to be double bond. Now in this case, what I've put here is different atoms around, but sometimes you can get similar groups around it. Maybe you can get like if I was to take this one as the hydrogen, then maybe this another atom, this another atom, this another atom. Yeah, this one is showing different atoms around. Yeah, so this is going to be a functional group called an alkene containing what? A double bond. All right. So now, what can you see of this molecule? There is something at the center. It's going to be said to be something like a triple bond. Maybe there's a bond is going to be better, but this is just an illustration. But essentially something like a triple bond. Perhaps if I can get another illustration of the same structure, what can you see here? Yeah. So there is a bond here. There's a bond here, and then there's a central bond, and then there are two bonds around it. This is another illustration of another molecular model for something which you call a triple bond, and it belongs to the functional group called alkynes. The bond angles are 180 degrees. It means that this structure is linear. This structure is linear, and the bond angles are 180 degrees. It's called an alkyne. The bond angles are 180 degrees. This structure is going to be said to be linear. All right. Okay. Now, there's another molecule here, which I'm going to call benzene, and benzene is an example of a more general compounds which are going to be calling aromatic compounds. They may not really have aroma, but what has been seen is that a good number of compounds that contain that showed aroma contained a benzene, but it's not to say all benzene compounds have got aroma. But we're going to see later the definition of aromatic compound. But what can you see from this structure? What can you see? It's got 1, 2, 3, 4, 5, 6. It's a hexagon, yeah. And this hexagon has got, there's a double bond, a single bond, and another double bond, a single bond, a double bond, and a single bond. So what can you see? So it has 3 double bonds and then three single bonds. Now, what can you see about this structure? It is lying flat on a plane, just like the ones which you're going to say with the double bonds, yeah. In other words, you're going to see benzene being a special type of an alkene, yeah. An alkene is one in which it's got double bonds, yeah. Can you see well? This is the good thing about a video show. You can be able to see a molecule very close, the way if I was in a lecture theater, you'll not be able to see these structures the way I'm actually showing. So it's an advantage to have this this session being zoomed on a video. It's very critical for your learning. So this is what we are going to be calling benzene. Now, there's another structure here. Perhaps I'm going to remove another atom here to be able to really show. Take for example, the black one is carbon, the white ones as hydrogens, this one as being oxygen. So this one is also hydrogen. Now, this structure is going to be related to the structure which I'd shown earlier, like the structure of water. Yeah, can you see that? So the thing is, one of the hydrogens has been replaced by a carbon containing hydrogens to it. Yeah, otherwise the structure is the same as water. Can you see? This is what it's bent, and then one of the hydrogens has been replaced with a carbon containing atoms around it. So this is an example of a type of a functional group called alcohol. So alcohols, in other words, they are related to water. Yeah. So it means that there is one of the hydrogens which has been replaced with a carbon containing structure there. And then you're going to see alcohols are going to be related. Please look at this structure in which I'm going to replace one of the hydrogens, the ones at the end which I've removed there, with okay, let me put it here. So I've now removed okay, let me bring it back so that everything will be clear here. So this is what I had the structure of my alcohol. So what I've done is to remove that hydrogen at the end, and then I've now attached another carbon containing hydrogens. Yeah. So now this one is still related to water, but now all the hydrogens which were attached to the oxygens have been replaced by carbon. So this type of compound we are going to call an ether. You're going to call it what? You're going to call an ether. Yeah. So there's another functional group which I'm going to show you. Yeah. There's another functional group here. Now, just for simplicity, I've just put a green ball to represent something which you call halides. Halides are in the former group 7, the former periodic table. Currently, the periodic table is much more complicated, but initially we had group 1, group 2, group 3, group 4, group 5, group 6, group 7, which was the halogens, and then group 8, which were like the noble gases, yeah, and the rest. So, but now things have expanded. There is group 2A, all those kind of things are a bit complicated, and you need to know more about the new periodic table. But now, take this as the halogen, like the halogens, like the which one? Fluorine, chlorine, bromine, iodine, and the rest, yeah? But for the current organic chemistry, we're going to focus on only 4 halogens: fluorine, chlorine, bromine, and iodine. So in this case, this structure is what I'm going to call, I'm going to do what? I'm looking for my white paper. It's going to be like a tetrahedral, in which one of the halogens has been replaced with a halogen. So this is what we're going to call alkyl halide. You're going to know, we're going to show exactly what we mean by the alkyl group. Yeah, I'm going to mention that in another video. So this one is going to be said to be an alkyl halide. Okay. All right. So there is another functional group which I'm going to show you here, in which okay, let me see. Okay, so let me try to remove one of the atoms here. Okay, so there is a carbon with a double bond attached to the oxygen there. All right, and then so this kind of compound is going to be said to be an aldehyde, carbon with an oxygen there, and then it's going to be related to another one in which the carbon double bond does not have a hydrogen. So this one is going to be said to be called a ketone. A ketone is going to be similar to an aldehyde. In a ketone, there is no hydrogen attached to the carbon. Yeah. And then let me just try to see whether I can get an amine. Okay. Right. Good. Let's just take the blue ball to be nitrogen. Nitrogen for an amine. Can you remember the structure which I showed you for ammonia? So this one is going to be said to be an amine. An amine is related to ammonia. So one of the hydrogens has been replaced with a carbon containing hydrogens to it. So this is going to be a structure of an amine. Yeah, can you see? Yeah. So there is a nitrogen with 3 bonds. One of the centers going to have the lone pair, and then there's the carbon with the 3 bonds attached to it. So this is an example of an amine. Then the last functional group which I want to show you is called a carboxylic acid. Yeah. What can you see here? There is the carbon with the oxygen with the double bond, and then there is oxygen with the hydrogen, and then attached to it there is the carbon with hydrogens attached to it. Yeah. So a carboxylic acid contains many functional groups in one. For example, it is similar to, like, there is the water in which there is the carbon with the hydrogen to it. Then it is similar to something like a ketone in which there is the carbon with a double bond. Can you see up to this side is almost the same, and then in this side is where it's a bit different. Yeah. So this is the structure of something you're going to call a carboxylic acid. What you're going to see is that carboxylic acids are going to be similar to the other acids that you have dealt with, like hydrochloric acid and sulfuric acid and nitric acid and the rest. The thing is this: there is this hydrogen at the end next to the oxygen, which can be lost. Yeah, in which you're going to be left with an ion, and then there is the H plus, which is going to be left. So this one is going to be said to be a proton donor, though it contains a carbon group. So it's called a carboxylic acid, but it's a structure which can donate a hydrogen. Yeah, all right. So it's going to be said to be a carboxylic acid. All right. So these are the functional groups that you're going to be dealing with. Can you see here? Alkanes. Alkanes, in other words, can be said to be organic molecules without a functional group. Yeah, because it only contains carbon and hydrogen single bonds. You can see in an alkene there is a center of electron density. There is the double bonds got electrons concentrated here. A triple bond has got two double bonds. Benzene has got double bonds here around it. Alcohols has got an oxygen with the lone pairs. Alkyls have got a halogen attached to it, like a chlorine, bromine, which brings something like electronegativity. And aldehydes has got a carbon oxygen double bond, a ketone similar. And amine has got a nitrogen in which you can form amines and ammonium salts and the rest. And then there's the carboxylic acid which can donate electron. But nothing can be said to be like the alkanes, in which so in other words, alkanes do not contain a functional group. It's just a hydrocarbon as such. Yeah. So we're going to learn more about alkanes in the next video. We're going to look at alkanes and particularly the structure of the hydrocarbons. Yeah. I believe you've learned a lot, and you're really going to enjoy more about this mode of teaching, in which you can be able to see the board close. Previously I've had issues of some students with glasses and the rest, and for some reason they have been coming to lecture rooms late, and then they see that they've got to sit at the back of the lecture theater and they cannot see the screen or the board well. But now in this one you'll be able to zoom in, and everybody will be able to see the whatever is being illustrated well. Yeah. So I hope you've really enjoyed this illustration. But once again, my email and the mobile number being given to the class rep, so you'll be able to get to me and be able to give clarifications. Yeah. So thank you very much. You're going to stop here on this section of the video. There will be more illustrations later regarding the hydrocarbons in a short while. Yeah. Okay. So let's stop there for now. Thank you.